Hi, I'm Debra Fischer from Yale University, and I'm talking today about the fundamentals of radial velocity precision for the Sagan Summer Workshop. Here's an outline of my talk. It's going to fall into three categories. The first is I want to talk about the progress that we've made to date. There's been good recovery of planets that are similar to Jupiter and Neptune's, but Earth's at all separations are really missing except around the very lowest mass stars. I think that most scientists are actually risk averse. I polled the Sagan students a couple of years ago and asked them if they had telescope time in the coming semester and they could use it for whatever they wanted. Would they choose to design a survey to look for Neptune to Jupiter mass planets where they would be assured of some success? Or would they want to look for Earth-like planets, which would be a long shot? It might fail. We care about the low mass planets because as far as we know, Earth mass planets in habitable zone orbits offer the best chance for life. We could be wrong, but that's our best guess right now. There are no other methods that will be better at finding Earths until we have something like a LUVOIR mission that's been launched. So right now, extreme precision radial velocities are really our best chance. However, this has been difficult because the radial velocity signal is tiny, right? Earth induces a velocity of 10 centimeters per second in the sun. And that's just not possible to detect with a precision of 1 meter per second. I think that aggressive progress on this front has been stalled by a widespread belief that stellar noise is intractable, and it kind of comes back to being risk averse. And then finally, I want to end by talking to you about the future of extreme precision radial velocities. Our results and the results from Espresso show that we're reaching 25 centimeters per second with this next generation of spectrographs. So that's something to be hopeful for. I think that the whole suite of talks that you're going to hear over the next couple of days is really important for understanding the role of instruments, telluric contamination, and stellar activity on our ability to recover tiny signals. So here's the progress to date, which shows a well-known plot of the planet mass, or M sin I, on the y-axis versus year of discovery. And you see that astronomers are so clever that the detected signals have been getting smaller and smaller with time. This is no accident. I think that one of the most important advances was the HARPS spectrograph, which really ushered in an era of 1 meter per second precision for radial velocities. Among the lowest mass planets, they actually orbit low mass stars, so the gains here don't really reflect an improvement in radial velocity precision yet. So HARPS moved us from 3 meters per second to 1 meter per second radial velocity precision, but there really hasn't been a notable improvement in radial velocity precision between 2003 and 2019. We know what the underlying population of exoplanets looks like from Kepler. At least for planets with orbital periods less than 100 days, Kepler was relatively complete. I've drawn in dashed lines which indicate the radius for Jupiter, Neptune, and Earth, and I can divide this plot into three sections. It'll be blue, orange, and green. And you see a sort of diagonal sensitivity in the green zone. This is for two reasons. First of all, the Kepler reaction wheel failed. The second one failed. But also, the transit probability decreases with semi-major axis. So this also reflects a lack of sensitivity to longer period planets with the transit technique. If we calculate the ratio of planets in each of these zones, I get something like 1.9 to 1 to 8.3, right, in the green zone. So Kepler showed us that low mass planets outnumber the planets in the sort of Neptune to Jupiter zone planets by quite a substantial amount. Now, what if we have an instrument that delivers 2 meter per second radial velocity precision, and we collect lots of observations? Then we would end up with a planet population that looks something like this. Now I have planet mass instead of planet radius on the y-axis, and orbital period still, and I've dashed in Jupiter, Neptune, and Earth, and divided these into zones again. So here you see a line of constant k, or radial velocity semi-amplitude of 3 meters per second, and with 2 meter per second precision, you could detect objects, planets that have masses that place them, and orbital periods that place them above this diagonal cut. You'd be missing quite a few planets, though. If you look at the ratio of planets detected in these three zones, it's 0.9 to 1 to 0.7 in the green zone. So if your spectrograph delivers 2 meter per second radial velocity precision, you're missing 92% of the planets in the green zone. If your radial velocity precision is 0.8 meters per second, so this is what is delivered by HARPS and other modern spectrographs, then velocity amplitudes that are larger than 1 meter per second can be detected. We look at these zones again. There's our old velocity amplitude line of 3 meters per second. But now, with a velocity precision of 0.8 meters per second, we can detect almost every object that's above this diagonal, lower diagonal line, right? So we can begin to detect more of the planets in the green zone. And now the planet ratio is 0.9 to 1 to 2.5. So in all these cases, I'm normalizing to the orange band, the orange zone. And you can see that we're still missing quite a few planets at low mass. If your spectrograph delivers 0.8 meters per second precision, you're still missing 70% of the planets in the green zone. But if we had 0.2 meters per second, and we employ some statistical techniques to take care of photospheric noise, we should be able to recover the Kepler exoplanet statistics with radial velocity methods and get much closer to detecting Earth mass planets in habitable zones around, let's say, K-dwarfs. The obstacles to higher precision are outlined in a paper, Fischer et al., 2016, State of the Field for Extreme Precision Radial Velocities. The first one is the instrument, right? The temperature changes, pressure changes are going to change the spectra that you get. But also our ability to carry out precise wavelength calibration and the quality of the CCD detectors that we use are important. The second obstacle is the information content, so the signal-to-noise ratio of our spectra, the spectral resolution, and the sampling or the observing cadence that we use. The third category consists of analysis errors. So these may be things like our ability to model the radial velocities, to understand the impact of the line spread function, telluric contamination, our ability to extract tiny signals from noisy data. The fourth category, which has really overwhelmed astronomers for some time, is astrophysical noise. This includes spots, pulsations, granulations, meridional flows, or global magnetic fields that change on solar-like cycles of 4 to 10 years. The global magnetic field strength can be diagnosed with spectral indicators like the calcium-2 H and K line core emission, or line bisector variations in the cross-correlation function, or emission in H alpha, or the full width half max of the cross-correlation function. So these are relatively crude and also global indicators. I think that we can do better than this. And one of the results which has really inspired me is Davis et al. Alan Davis was one of my graduate students, and he carried out an extensive number of simulations. So looking at principal component analysis at the pixel level in simulated SOAP spectra. These plots show the effect of the number of principal components that can be recovered. This is essentially an indicator of the information content in the spectra. And you can see that for spots and faculae that in the top row have 5% surface coverage, which is pretty extensive. That's a young star. That you can really, with high resolution, high signal noise, you can really get a lot of information to be able to model those surface radial velocities. In the middle row, you can see spots or faculae that are covering about 1% of the star. And in the bottom row are really the chromospherically quiet stars, like the sun, or even quieter, that we're used to looking at. And for each of these subplots, he's carried out a simulation, a grid simulation, where the grid covers the resolving power of the instrument on the x-axis and signal to noise on the y-axis. And for most of the work, most of my career, I've been sort of working at the 50 to 60 resolving power, so that's Keck high-res or the Lick-Hamilton spectrograph, and signal to noise of, I don't know, 1 or 200. And you can see that for really almost all of these plots, that doesn't give us the fidelity of information that we need to ever begin to see the activity indicators differently than the radial velocity measurements from orbits. So this result gave me a lot of hope that the photospheric radial velocities could be disentangled from the orbital radial velocities, that they are imprinted line by line in the spectra differently than the orbital radial velocities. That's what this simulation tells us. We designed and built Express, the extreme precision spectrograph, which is at the 4.3 meter Discovery Channel telescope. Our goal was 20 centimeters per second precision. That was for the instrument. The instrument was funded by the National Science Foundation, and the total cost for the instrument was $6 million. We had a small but amazing team of graduate students and postdocs and research scientists who worked on this. It's been an incredible journey. There are a lot of unique features about Express, and I'll let you read them, but the top ones, I think, are the laser frequency comb, which is, I think that Express is the first optical spectrograph to use an LFC full-time for radial velocity measurements and exoplanet detection. And I know that the LFC was tested at HARPS and has been used there as well. We also went with higher resolution, motivated, I think, by Alan's work, Alan's simulations, and our intuition. And like HARPS, Express has a vacuum enclosure, precise temperature control. It's built with an INVAR optical bench because INVAR has a low coefficient for thermal expansion. We use octagonal and rectangular fibers with pupil slicing to take our circular pupil from the octagonal fiber, slice it in half into 2 half moons, stack it and inject it into a rectangular fiber. So the rectangular fiber is really essentially our slit that's being injected into the spectrograph. And then we have a number of other important designs. The wavelength weighted, the chromatic flux correction for barycentric observations was important. Our detector, I think, was important. Our telluric modeling advances have been really important. And then ultimately the telescope itself. So the LDT or DCT has a deployable tertiary mirror that rotates between 5 instrument ports. And in 1 minute, we can be changed from observing with a different instrument to observing with Express. Express comes up very quickly, and we're online and off and running. And that means that we can do strategic scheduling of our observations. That is really important for special cases. I want to say that this instrument was designed as an experiment. I really hoped to contribute to the field and to the understanding of what it takes to get extreme precision radial velocities. To achieve these goals, we restricted our sample size to stars that were brighter than 7th magnitude. We knew we wanted high signal to noise. We can look at fainter stars, but the precision just won't be as good for those stars. One of the important factors is that we do fiber scrambling. And Ryan Petersburg is one of my graduate students who invented this. You can see double-armed fiber agitator. It oscillates at different frequencies to give chaotic scrambling of the modes in the fiber. And here you can see some results. This is just to show you, like, really look under the hood and see how hard it was back in December of 2018 when we took our 1 hour of laser frequency comb observations and expected to get centimeter per second precision, and instead saw this huge sinusoidal variation. Right? The RMS of our data with 1 hour of laser frequency comb was 6.5 meters per second. Completely like game over at this point. Fortunately, Andy Shimkowiak on my team figured out that there was a beat frequency that was occurring between the spatial light modulator and the laser frequency comb, which was essentially strobing, and vibrations in the cryocooler for our detector. So he then went in and he reprogrammed the spatial light modulator to run at 55 hertz instead of 60 hertz, and the beat frequency period dropped to below a second. Problem solved. So by January, we thought we were finally fixed. Everything would be good. We'd be down to centimeter per second precision. But you can see in that middle blue set that the RMS is still 30 centimeters per second. That's when we discovered that the low torque motors on our fiber agitator were frozen because they had become tangled with the fiber. We fixed that, built a new design for the fiber agitator, and by February of 2019, we were finally on sky with the precision that we wanted, an instrumental precision of 5 centimeters per second. This is an hour of laser frequency comb observations cross-correlated against each other. So getting to this high precision is all about like calibration. Here you see the rectangular, the image of our rectangular fiber with the laser frequency comb going through it. And about every 10 pixels, we have an LFC line. Here's the interface for the laser frequency comb showing you the flattened flux as a function of wavelength. And here's how we started modeling the laser comb. We would extract the spectrum of the laser comb. We would do a peak, use a peak finding algorithm, find the center of the peak, assign that to the known wavelength from the laser frequency comb, and then interpolate the wavelength solution for every pixel on the detector. But the instrument is incredibly stable. The LFC is stable. Express drifts about 1 meter per second over a full night of observing. So we have a new approach that's been developed by my student Lily Zhao while she was at the Flatiron Institute in New York City working with David Hogg and Megan Bedell. And the idea is that they're using a principal component analysis to do a low order transformation of the wavelength solution through the night. So avoiding having to come up with a complete unique solution every time, I think is going to make this more robust, and we are now testing our radial velocity measurements with Excalibur. Here's some data taken from Express in 2019. I'll just flip through a few stars, HD 99491. The internal error bars are about 20 centimeters per second, and the RMS over 100 days or so is about 70 centimeters per second. Here's another star where the internal error bars are ridiculously low. It's a bright star, and we have like roughly 10 centimeter per second precision. And the RMS is over a month is about 4 centimeters per second. I can hardly say that. It's amazing. With time, as we accumulate more velocities, we're seeing more variability, and we're working to figure out where that's coming from. But so far, nothing's been done to these radial velocities. We're not using any Gaussian process regression. We're not using anything to disentangle the photospheric velocities at this point. We're simply observing the stars, checking what our internal error bars are, and the RMS, and this is kind of out of the box what we're getting. Another case. So those are sort of typical. So of course tau Ceti is the poster child for high precision, and with all of our other spectrographs, high res, the Lick-Hamilton spectrograph, tau Ceti was the star that really delivered high precision. But we can see a sort of a problem here. Although the internal error bars are about 10 centimeters per second, the RMS over a couple months is almost a meter per second. So there's some problem going on. And if we zoom in, these nightly bend data points are actually varying quite a bit. So Tau Ceti is a bright star. The exposure times are 20 seconds, something like that, depending on conditions. And so we're freezing out the P mode oscillations in this star. That's great for doing science with P modes and astroseismology, but of course that's not what we're after when we're looking at our stars. Okay, when you write a proposal for a spectrograph, you're going to make your best guess about radial velocity, what the radial velocity precision will be. Then you'll build the instrument and everybody will be asking you, why haven't you reached that precision yet? It's hard to know when you're designing the instrument until you actually build it, what you're going to get. And then once you do take measurements, how do you know where the errors are coming from, right? The radial velocity error budget is very complex. It's the kind of like the terms are not exactly orthogonal, but more or less it's the quadrature sum of many terms that come from the instrument analysis, photon noise. Once Express was commissioned, my student Ryan Blackman did a beautiful job trying to isolate as many of the contributions to the radial velocity error budget as possible. He did not include stellar activity in his analysis, but if you look at his paper from 2020, you can see that the instrument errors are less than 10 centimeters per second. This comes from the laser frequency comb stability tests. Photon noise, we know that our radial velocity precision is a function of the signal to noise, and at signal to noise of 250 per pixel or 500 per resolution element, we hit a photon noise limit of about 30 centimeters per second. And that's as measured on sky, on star with radial velocity measurements, short term. So the single measurement precision that we get with Express then is something like, we expect something like 30 centimeters per second, and has been validated now by the work that, that Ryan Blackman has done. We have a proposed benchmark for the community, for the EPRV community, and that is the star HD 3651. As I said, the radial velocity error budget includes many terms, and one of them is the possibility of undetected planets. So the nice thing about HD 3651 is that this bright star has a known planet. It's roughly a Saturn mass in an orbit of 62 days with very high eccentricity. The star is accessible from the north and the south. No excuse for not observing this star. And it's a chromospherically quiet K-dwarf. Okay, so there'll still be some stellar noise, but it will be reduced. The key is that the dynamical simulations that were carried out by my student Sam Cabot, working with Greg Laughlin, show that any inner planets would be dynamically cleared away by this Saturn mass planet. So you have a unique opportunity to say that the velocity errors are coming from your instrument, your analysis, and the star. And it's a relatively, as I said, chromospherically quiet star. You've eliminated the possibility of short period planets, and that's what makes this a good benchmark for EPRV instruments that are coming online. So here's the case. Here are the data for HD 3651 that were collected, the historical archival data from Keck Hi-Res, presented in Butler et al. 2017. Their individual error bars were about 1.2 meters per second on this 10-meter telescope, and the RMS to the fit is about 3.4 meters per second. With Express on the LDT, our internal error bars are about 25 centimeters per second, and the RMS is about 60 centimeters per second. And you can see here that this is just this is about 6 months of data. So we got about 2 orbital periods that are phase folded here. And you can see that this is where the deployable tertiary really came in handy, because catching periastron passage, that short rise, right, from the bottom to the top at about phase 0.4, that's really tough to get. And in all of the time of Keck that the star was observed from Keck, something like 15 years, right? There are very few points there along that region. We were able to strategically request 10 minutes to observe this star and to pick up those data points. So that's the kind of value of high cadence and the ability to control the scheduling on the telescope. These results are presented in a paper by John Brewer that just came out this year. The Geneva team has a beautiful result with Espresso, and these data for Proxima Cen show observations collected with UVES, with HARPS, and with Espresso. There were 2 eras of Espresso. So in the filled green circles, you see the final fully commissioned state of Espresso, and you can see the earlier data in the unfilled green circles. And then a backdrop to the Espresso data shows you the HARPS data and the UVES data. So yes, with HARPS, you can take 450 observations and phase fold it and find this planet. Great. With Espresso, you can take a couple dozen data points and find this planet. So you find them more quickly, more robustly, more cleanly. You can separate out multi-planet systems and reduce the impact of astrophysical noise because you're looking over a shorter time baseline. I will say that in these data sets, the team, Mascareno et al., in this paper 2020, used a Gaussian process regression to remove some of the noise, to drive, and that's going to drive down the RMS and is worth discussing with Vinesh Rajpal when you're listening to his talk on GPs. So, but still, the residuals are incontrovertible, right? The UVES residuals are 80 centimeters per second. HARPS residuals are 1.3 meters per second. Proxima Cen B is a faint star, right? And Espresso, the residuals are 30 centimeters per second. So that's really spectacular. In summary, the precision radial velocities that we've used for the last 20 years have been successful in detecting Neptune to Jupiter mass planets around nearby stars. They've had the state of the field precision has been about 1 meter per second for the last decade or two. And lower mass planets are detected, but they're around later type stars, so lower mass stars. It's not that the precision is improving, it's just that the amplitude is larger because the stellar mass is lower. There's a new generation of EPRV instruments that's now online. This includes Espresso and Express. And soon, the newest spectrograph will also be online. And these instruments are uniquely delivering extreme precision radial velocities of about 25 centimeters per second. I want to emphasize that the Menlo system laser frequency combs are now turnkey. The one thing I would wish for is to have precise calibration blueward of 500 nanometers. The combs really go from about 500 to 700 nanometers right now. And then you can have infrared combs that are robust too. So there's been significant progress, which I have not discussed, on statistical methods to disentangle photospheric radial velocities from orbital radial velocities. And you'll be hearing more about this in the workshop. I just want to emphasize that you have to get everything right. The instrument has to be very stable. The extraction has to be near perfect, right? Beautiful flat fielding is required to make the most of the detectors that we have. The wavelength calibration is critical to telluric modeling. But you can see from both Proxima Cen and from the latest results from Express on HD 3651, we have more coming out soon, that we really have reached this new goal. So I just want to end by thanking my team because this could not have been done without these amazing people. Colby Jurgensen was the optical designer for Express. Tyler McCracken wrote all of the code for driving the motors. David Sawyer was the project manager. Andy Shemkoviak solved every problem with laser frequency combs. And my graduate students, Lily Zhao, Ryan Blackman, Brian Petersburg, Joel Ong, Alan Davis, have all been amazing. Christopher Lee was an undergrad who wrote the telluric, empirical telluric modeling code. Renee Rasmussen visited us from Denmark, and grad student San Cabot Zhen Zhu was a student of Jesse Szewski, who's a stats professor, and her student Parker Holzer and postdoc Bo Ning contributed a lot. And Lars Boucave has been an amazing source of information. And I want to thank all of the instrument builders too. When we got stuck, I reached out to Andy Senyorgi, to Subrath Mahadevan, to Francesco Pepe, and every one of them was generous and kind and thoughtful and really helped us to move things along. Thank you.